Hi, welcome to my INTERSPEECH 2021 presentation. Today I will present the paper Speech Decomposition based on an hybrid speech model and optimal segmentation. My name is Alfredo Esquivel. I'm a PhD candidate from the Audio Analysis Lab at Alfredo University Brno, and this paper is co-authored with Jesper Nielsen and Christensen. So let's start with the presentation. Great. So in this paper, we assume that the speech follows an hybrid speech model, which there is a deterministic component and a stochastic component. The deterministic component, which is also the periodic parts of speech, or the so-called voice speech, is described by an harmonic model, in which we have a fundamental frequency of pitch and different harmonics or sinusoids, which have a frequency which is an integer multiple of the pitch. There is a total of L harmonics, and it's also known as the model order. By the other side, the stochastic part of the aperiodic parts is the so-called on-voice speech, and it's better described as an autoregressive process. And this component accounts for phenomena such as turbulences or friction. And both components can coexist, and because they are of different nature, that is why the model is called hybrid. Because this is more peaked spectrum, and this is more continuous or smooth spectrum, the autoregressive one. And the extraction of both of them is very useful in applications such as speech coding, synthesis, or diagnosis of illnesses. The problem with some state-of-the-art methods, such as 1 and 2, is that they don't distinguish between on-voice speech and additive noise. When they extract something that is so-called stochastic, everything which is stochastic is integrated in that extracted component. But for example, in telemedicine applications to diagnose illnesses from speech, for example, this differentiation between on-voice speech and background noise is necessary. And there are some problems with this state-of-the-art methods. For example, they don't estimate the number of harmonics. One of them is based on the capstone, which is not very robust to noise and converges to the work solution. And for example, one, which is more recent, it whitens the parallelogram, which is quite good for pitch estimation, but it doesn't use adaptive windows and does not estimate the number of harmonics. Yeah, so here we have an example of the decomposition on a clean speech signal using our proposed approach. So for example, here is the voice part and the extracted on-voice part. For example, here at around 2.1 seconds, we see that the harmonics up to 3 kilohertz are correctly extracted in the voice part, even if there is some weak harmonics between these fundamental and these big ones. And yeah, for example, here, you can see that there is coexistence of both harmonic and stochastic components. Actually, by our method, we are able to detect this around 1, 2, or 3 harmonics, and the other parts is the stochastic parts. And actually, for a better abstraction, as we will show later in the results, it is better to use time-variant segment lengths or adaptive segment lengths, which have a better feature-specified model, as opposed to using the traditional fixed segment lengths. For example, if the pitch remains constant, for example, let's say around a frame of or interval of 600 milliseconds, the pitch still keeps its value at 178.5 hertz, for example, then the segment length should be longer than the typical fixed length. For example, should be around should have a bigger value than, for example, if the pitch is changing too fast. If the pitch, for example, goes suddenly from 126 to 129 hertz, it's indicative that the pitch is changing too fast. So we should use in such region shorter segment lengths. So for a better extraction, we claim that and we show that it is better to use adaptive segmentation. But for doing that, we need to estimate the segmentation markers and the optimal segment length. But that requires, therefore, to estimate all the parameters of this deterministic and stochastic parts for all possible candidate segment lengths before finding this optimal segment. And we use a priori information of autoregressive parameters of on-voice speech and noise. So yeah, this is the mathematical model and the filtering for the decomposition. So the speech is described by the voice part, described by the harmonic model, and the on-voice part, which is an autoregressive process. But in additive noise, we have this noise term, color noise term, and this on voice and color noise is added together in the stochastic component of speech. And the goal is, given noisy observation, we want to extract the voice and the on voice signal. And from when we apply in this filtering, we base the statistics on M samples, where M is less than the number of N samples, the number of samples in the segment length. And because the components are uncorrelated, the covariance matrices are added. And sometimes if we prefer the processing in the frequency domain, we can use the PSD representation. For example, here of the stochastic part is decomposing the on voice and the noise PSD. So first, if the segment is voice, if we have a pitch, we want to extract the voice component by applying a filtering matrix to the observation. So the undesired component, of course, is X, the fully stochastic component of the noisy signal. And this is done from a joint diagonalization of the covariance matrices. And we use M eigenvectors and eigenvalues to form a linear filtering matrix. And after we have extracted the voice part, we have the model residual, but here is in the frequency domain because we are taking prior information into account. So we apply a binary filter, which is HU, in the frequency domain, which uses prior information. Yeah, we need now to estimate these covariance matrices, these RB and these PSDs. And well, before going to that, the voice part is described by an harmonic model, as I said, in which we have L harmonics. Each harmonic has an amplitude, a complex amplitude, expressed in terms of the real amplitude and the initial phases. But this model is more accurate for a length of, a segment length N opt, an optimal segment length. So we should find this optimal segment length. But before, we need to estimate the parameters for all possible candidate segment lengths. So we stack M samples in this vector, which is set alpha, where set is a vector, is a matrix containing the Fourier vectors. In each of its columns contains these complex exponential vectors associated with the different harmonics. And this alpha is the vector containing the amplitudes of the different harmonics. The voice part is described by this autoregressive process, which these beta UIs are the AR coefficients. And this is the excitation-wide partial noise process of variance sigma E squared used to generate the voice component. And also CN is modeled as an AR process with different gamma CI AR parameters. So of course, we need to find these amplitudes, this pitch, and these excitation variances, and the AR parameters. Yeah, so we have here how the voice part covariance matrix is estimated, because this holds for an optimal segment, which is more accurate for the model that holds, is more accurate this covariance matrix. It depends on the covariance matrix of the amplitudes, which is given in this form. But before doing the extraction of the optimal filtering, we need to estimate the, well, in reality, we need to estimate the pitch and the linear parameters from the optimal segment length. But before doing that, we need to estimate the parameters for all possible candidate segment lengths. And after doing that, we choose an optimal segment length. And this will be the one which maximizes the posterior probability of the rate. I'll go further into this. So how do we estimate the parameters? Either from the optimal segment length or for all possible candidate segment lengths. So it's a joint parameter estimation problem. So we need to estimate both the harmonic and the autoregressive parameters. So it is based on a white Gaussian-based method, which this assumption may be quite simple and not unrealistic, but is efficient in a computational way. And this is a non-linearly switched pitch estimator. But to apply this method, we need to pre-process the signal. Speech enhancement usually is what people think that one should do to extract better features or some parameters of the signals, but actually in this method we assume the noise is quite Gaussian, so we need to apply some method which counteracts the spectral shape of the noise, the autoregressive spectral shape of the noise. That's why we use an autoregressive whitener. The question also here, which is related to some other contribution of a journal paper we just submitted, is which whitener gives more reliability to this square speech estimator. So typically this is the noise statistics are estimated using noise trackers, and one can fit the noise piece into an AR spectrum and apply the inverse spectral shape to whiten the noise component. And this approach may work well for stationary noise, but for non-stationary noise, such as bubble or residual noise, we should take into account spectral shapes, for example, in a dictionary. And this we can show that maximizing the likelihood is equivalent to finding the activation coefficients of the spectral shape in a parametric and a mathematic. And this will give a much better capture of the noise spectral envelope and therefore allows a higher noise flatness and a better pitch estimation accuracy. But this is more related to this contribution that is quite important for obtaining much better parameter estimates. And yeah, because if we only did that, we would only have the AR parameters of the noise. But actually, we are interested also in the AR parameters of the full stochastic sequence, which also includes the on-voice component. And also we can further improve the pitch estimates because it may not be this single cascade the best solution. So we can post-process the resulting estimates in iterating between two steps. Of course, after we estimate the pitch, we can select a number of harmonics using model comparison criteria, and we have a model residual and its AR parameters. So these AR parameters now also include the contributions of everything which is stochastic in the noisy signals. We can pre-whiten again the signal and iterate between these two steps until convergence. But this full model residual has a parametric spectrum which has the sum of two components of the on-voice PSD and the noise PSD. And we need to find these excitation variances and these autoaggressive parameters. And this is motivated by this paper, in which a single code entry of on-voice and noise will be chosen, such that it is the one which minimizes the cross data between the observed spectrum or periodogram and the model spectrum. And after finding this entry, we can form a linear filter to extract the on-voice part of speech. But as I say, this has to be done on segments of optimal length. So before doing the filtering, we need to find the optimal segments. And each way in which a signal can be segmented, which consists of a segment K and in samples, we define a minimum number of, or a minimum length of a segment. And it consists of an integer number of this minimum segment length. Is a model, and the set of candidate models is denoted as M. For the voice pitch, it is used the maximum a posteriori criteria to select the model which maximizes the a posterior probability. So one can choose from either this cost function, which consists of a likelihood and a model penalizing terms, or this cost function if there is no harmonic in the signal. And this allows to obtain segmentation markers of the voice pitch and the optimal segment length. And I will describe how this is done, or briefly mention it. But after we have extracted the voice part, the residual will be segmented according to this log likelihood J to N function, which depends on the excitation variances and the error parameters. And this allows to obtain segmentation markers of a voice pitch and optimal segment N opt prime, which is different from this N opt. And one should compare all the possible cost functions for the segment length. And yeah, this is what is done for either J1 and J2 from a minimum segment length. And of course, we have a subsegment of any samples, and we should divide the segment into S subsegments. And here is the segmentation algorithm, and it is you can further refer to this paper. And essentially, it's replicated here and how it is done. But at the end, after we reach the end of the signal, we should do some back tracing to find the best segmentation. Yeah, here is a summary of the steps of the decomposition. So basically, it applies to estimate the parameters for all possible segment lengths and finding the optimal segmentation markers and the optimal segment length. And then we have to estimate the parameters again, but inside the optimal segment lengths, because we know that the models are better fulfilled there. But yeah, it can be quite consuming in time consuming, and it should be done in an offline processing in its current form. So here we have some experimental evaluation. Which, for extracting the ground truth of the voice pitch, we use segment lengths that go from 20 to 50 milliseconds, which is 160 to 400 samples for a sampling frequency of 8 kilohertz in steps of 40. So we don't use, for example, in this algorithm, we have the B, which is the number of sub-segments from the minimum segment length, which is 5 milliseconds, because we start at 20 milliseconds. So the cost function for 5, 10, or 15 milliseconds is set to infinity, because the pitch estimator will not work well in the case that you have a low pitch in segment lengths of this duration, this too low end. It may work well for high fundamental frequency because it's trying to pass, and we can have a 2 or more periods, for example, in such cases, in very short frames. But for low pitch, the pitch estimator will not work well. And the maximum number of subsegments is set to 10. And the dimensions of the filtering matrix are 40. And we chose this because we know that 40 is a divisor of all these possible segment lengths, and it facilitates the processing. And it actually matches all the parts of the signal very nicely. And it is updated, this filtering, every 20 samples, which means that there is a 50% of overlap. And after we extracted the voice part, we subtracted from the clean speech signal to get a ground truth of the voice part. And from this one, using, of course, different samples that we use from the testing, we have we train an auto-regressive codebook of 64 AR entries, which we use 160 samples for the training. And here we have an example of a speech signal excerpt, a clean one. And we extract based on fixed segments and the optimal segmentation. So one sees, for example, the orange, which is from the voice part from the fixed segmentation. We are not able to capture this periodic part, which corresponds to voice pitch. And we can capture it, of course, if we use the optimal segmentation. And therefore, if we have a good extracted voice component, the consequence is that the invoice component is more stochastic, which doesn't happen if we use a fixed segmentation with some periodic part. But yes, in our mathematical problem, we are considering the problem of the noise. We added 4 noise types to 4 of the Chile files. Well, before, in this case, we use the criteria for segmentation based on the white noise assumption. So we provided the signal using the setup of algorithm to your submitted journal paper, in which we use 32 speech and 256 noise spectral shapes in the parametric MMF. You want to see why do we need too many spectral shapes for the noise. You can see the journal paper. And the segmentation of the voice part is obtained from segments of 50 to 40 milliseconds. And actually, well, here we used 64 for the on voice codebook, and we use for the binary filter defining the entries as 16 noise entries codebook. And we here compare the performance of the extraction against our ground truth that we already have to the noisy case, to see if the methods perform better than no processing the signal, using the fixed segmentations, which is the magenta curve, and the optimal segmentation, which is the blue curve. And the other 2 colors are the state-of-the-art methods. But because these methods ignore the presence of the noise, we apply speech enhancement based on an optimal modified LSA estimator. And actually, for segmental SNR, it is preferred a higher value. So we see that the blue curve is much higher than the state-of-the-art methods, and is higher than the processing based on fixed segments of 5 and 10 dBs. At 0 dBs, it shows similar performance in all cases. And lower log spectrum distortion for the voice speech component. Similarly, better results for a segmental SNR in the on-voice case. Also to the state-of-the-art methods. But here we see that the other methods, because they apply speech enhancement as pre-processing, they are able to achieve a lower log spectrum distortion as compared to our proposed framework, which indicates that we may further improve this extraction of the components. And just to conclude my paper, we have seen that the use of optimal segmentation combined with the parameter estimates of the hybrid speech model will allow to better recover the voice and non-voice components compared to using fixed segments. And and these adaptive segments will result in a better modeling of the periodic parts of the voice speech with a higher probability of improved segmental SNR, a lower log spectrum distortion for both components. And we use prior spectral information in the codebooks to differentiate between on-voice speech and additive noise. And in general, we see that a higher segmental SNR and lower log spectrum distortion for voice components is possible if we compare to state-of-the-art methods. But we have a potential to further reduce the log spectrum distortion of the extracted on-voice part. So we speculate that we should consider other filters in the variable spanning and filter framework, which is this paper. Or because of low SNRs, the on-voice component may be masked by which may be quite weak compared to the level of the additive noise might be masked. So we should probably include masking curves of perceptual criteria in the filter designs. So something we speculate from now. And also as a future work, we plan to derive the segmentation based on the recently introduced joint pitch AR estimator, which is not based on a wide torsional assumption. So we should redefine the equations of the segmentation criteria, for example. And also we want to evaluate how this framework or methodology works for applications such as sustained vowels in diagnosis of Parkinson's disease. So that's all. And thank you very much for your attention.